Good morning. Welcome back. Welcome to my sanctuary at home. I hope you had a great spring break. And if you have any good stories from spring break, send me an email and I'll share them with the class. I figured we could start with a semester review to get back on track after a long break. We'll be talking through chapters 13 and through 22 and all, and today we'll be talking about chapters 13 through 16, gases, liquids, and solutions. These boards are also on my teacher page. There are no vocabulary and homework for this section as we'll be reviewing a lot of material. All right, let's get started. First off, we'll talk about gases. Now, gases are these very spread out groups of atoms. There are some molecules in there, water vapor and all of these different gases, but as a general rule, gases break down at the atomic level. So individual atoms are flying around. They're moving fast. They're going as fast as that light will take them, near the speed of light sometimes. And they're free to move wherever they want until they bump into another one and they change direction and go flying out and they bump into somebody else. We measure our gases according to a couple different things. First one is the temperature, kinetic energy. When we're measuring our temperature, we're measuring how fast those different atoms are moving. How quick they're moving in each direction, all over the place. Different way to look at temperature, but we're measuring the speed, the kinetic energy of those atoms. The next area I'd like to talk about is the pressure. We're measuring these impacts. If you remember, all these atoms are slamming into you, bumping into you, moving you, pushing you away. And this pressure is a count, 1, 2, 3, 4, 5, of these different impacts as these atoms are hitting you. They're going to be moving. They're going to be moving fast. The pressure they exert is the amount of times that each of these atoms bumps into you. We measure these different pressures, whether it's an atmosphere, imagine that. The unit for measuring air pressure is called atmosphere. That's equivalent to 760 millimeters of mercury. That's that temperature. As it pushes it down, your barometer, your thermometer, they're measuring this temperature and pressure, the amount of times this amount of this mercury that the air can push up. Or in our metrics, as we try to convert to metrics, those kilopascals, named after Pascal, 101.3 kilopascals. That's our metric measurement. I've told you before that the only law you need to remember when we're dealing with the behavior of gases is the combined gas law. So this compressibility idea, the fact that these things are fast and free and move wherever they want, you can squish them together a little bit. And they don't really mind. It's not like they're going to run into each other anymore. You're increasing your pressure a little bit, but there's still room for these air atoms to bounce around. 4 different laws went into making this combined gas law. Boyle's law, that compares pressure and volume. Charles' law, volume and temperature. Gay-Lussac's law compares pressure and temperature. And Dalton's law says that when you have multiple different gases all in the same spot, you can just add those pressures up. Since they are fast and free, you can just continue to add more and more stuff in there. When you add these different pressures, they all combine into an individual pressure. So our final combined gas law, the pressure times the volume divided by the temperature at the start are 1, the first state, the pressure times volume over temperature, PV over T, is equal to the pressure times the volume times divided by the temperature at the end. 2, the second state, PV over T equals PV over T. So we come up with this combined gas law. Try and remember that one, because that one is actually significant and you will come across it again. The next board I'd like to talk about are concerning liquids. Let's start off with a discussion on changes of state. So as we're changing state between solids and liquids and gases, we're adding this energy that causes these things to move faster, increases their temperature, their kinetic energy, that these atoms are moving around. So in a liquid, they can move around a little bit. They're kind of constrained. We got them in our jug here, and this liquid has a bunch of atoms in that are moving around. As we put it over the burner, boil that water, we're adding energy. And each one of these different atoms, one at a time, speeds up. When you're adding the energy, you're adding the energy to the individual atoms. When this atom has enough energy to increase its kinetic energy, its speed, its temperature to a higher level, it turns into a gas. It changes its state from a liquid to a gas. Whether we call it evaporating, because when we boil water, we're really just speeding up the evaporating time. We're adding that extra kinetic energy, that extra force from outside, causing that thing to evaporate faster. Or it's freezing, changing from a liquid to a solid. That's when these energies slow down. And you're taking that kinetic energy away from these atoms, causing them to slow down. As they're slower, as they're moving less, they need less space, so they come closer together. They're not bumping away from each other anymore. So they're coming closer together and turning into a solid. Let's have a quick discussion on surface tension. As we had talked before, all of these atoms, the van der Waals forces, a thing we talked about last semester, those van der Waals forces are pulling in every direction. They got to latch on to something to pull in. So these van der Waals forces pulling in every direction, well, the ones on the outside, they're confused. They don't know what to pull on. So they flop over and double up this force, this pull, this bond on the outside of the water. When we say surface tension, we don't just mean the top. If it doesn't bond to the sides or the bottoms, you'll still have that surface tension all the way around the outside of the water or the liquid. And all of these different types of liquids all generate this same surface tension, whether it's water or metals, melted something, anything out of liquid. They all have this surface tension because these van der Waals forces, they got to grab something. So they flop over and grab that other atom right next to them, and they have two bonds instead of just one, and it's twice as strong. So that surface has twice as much cohesion as it's supposed to with the rest of the water. And all of these things bond up to create what we call surface tension. Talk a little bit about ice. We haven't talked about this. You know I love this one. This is one of our proofs of God. This bend, this L-shaped structure of a water molecule. The oxygen and the two hydrogens, H2O. It bends. These extra electrons sitting on top push that down, force it into an L shape. So that when it turns into ice, it forms all these structures. A bunch of empty space in the middle. There's nothing there. It's not like there's air in the middle, it's just an empty space. And because it has these empty space, it's less dense. So our solid ice is less dense than our liquid water, and that ice floats on top of the water. Otherwise, the oceans would freeze solid. As it froze, it'd sink, and the whole thing would be frozen solid. And the whole thing wouldn't work. We wouldn't be here. So this is one of those ideas that God came up with to make this whole system, this creation of His, work properly. One last board I'd like to talk about compares solutions and suspensions. Well, as water dissolves things, in this case salt, table salt, makes it into salt water. As water dissolves things, it pulls those bonds apart. Doesn't separate them. They're still contained into our sodium chloride. It's still a thing, but they're stretched out. So this sodium ion and this chloride ion go looking for a partner because now they're stretched out. They're unbalanced. And we know that the universe must be balanced. It's desperate for balance. So it has to have another charge to balance out these ions, get some positive. And it pulls it into solution, dissolves other things. So this solvent, the water, the thing that dissolves it, holds all these solutes, salt and whatever else gets grabbed up, into that solution. We have solvents and solutes inside the solution of water and salt. Okay? When we're talking about a suspension, these surface tension boundaries that we just talked about are all over the place. But when you have a particle inside that water, inside that collection of water molecules, these are all water molecules, okay? So you have this piece of dirt sitting in the middle there. Is it a solution? Well, if it's a solution, then all of these internal surface tension boundaries are strong enough to hold the weight of that particular molecule, that particular foreign substance that's floating in the water. If it's a solution, it stays there. It'll stay there until you take it out. So it'll stay there indefinitely. A suspension, on the other hand, so this clump of dirt floating in the water is too heavy for those surface tension van der Waals bonds to hold it up. So it snaps them, and this dirt clod falls out of the liquid, settles down to the bottom of the water. And we call that a suspension. When things are settling out, it's in suspension. When they're staying in, it's in solution. Okay? We'll come back with part 2 and cover the rest of our semester review, chapters 17 through 22. All right, see you soon.